Hello everyone, this is for section 9.1 for pre-calc. First thing I need to talk to you guys about are explicit formulas. I'll delve with recursive in the next couple pages. Explicit formulas are formulas that you're used to. That's the style. Say I were to go back in days of old and make a coordinate tree for you guys. So you pick an x value, say 2. You take that x value and you fill it in. So you have 6 minus 2 is 4. You take a number, you fill it in, you get a discrete means an actual concrete answer that you don't have to build on it. It's there, you're done. You fill the number in, you evaluate it, it's over with. Okay, that's explicit. Recursive will make more sense in a minute, so I'm not going to reference it right now. You're dealing with sequences and series. So an explicit sequence is a sequence of numbers. Say you have 3, 7, 11, 15, 19, and so on. The pattern continues. This is going to be the first term in the sequence, the second term in the sequence, the third, the fourth, the fifth, and so on term in the sequence. You can't have a negative third term in the sequence. No, this is a counter. It's an indice. In science class, when you make up a table, whatever it is, whether it's time and then, I don't know, the temperature, that your first observation is your first observation. That a first observation could be at time 0, but it doesn't matter. That's your first observation. It makes no sense to say observations that came before the first one. It's nonsensical, okay? This is your first term in the sequence. That's where the sequence begins. Okay, so why am I making a big deal of this? You have a sequence of numbers that starts here and extends off, okay? That is going to be your first term. This is your second term. This is your third, your fourth, and your fifth. These numbers that are written below are simply counters. They're indices. They tell you which term in the sequence it is. So instead of calling the equations y equals, like it was here, it's a sub n, and I pronounce the word sub, a sub n equals 3n minus 2. Whatever this variable is, that's the variable that's in the equation. So it's kind of like when you guys used to have f of x equals 3x minus 2. Whatever this variable is, there it is there. Well, when you're dealing with a sequence, it's a sub n equals, and then the n is somewhere in it. So rewriting this using this explicit sequence notation, this would be a sub n is equal to 3n minus 2. And this one would be a sub n is equal to n squared plus 6n minus 7. Now the understanding is the very first number you're going to fill in is 1. So then you'd have 3 times 1 minus 2, it's times in there, equals 4. A sub 2 is you're going to fill 2 in. Whoops, I made a mistake. Apologize. My arithmetic. Oop. So then, okay. Whew. Minus 2, that's 4. Okay, a sub 3, take a 3 and fill it in. So 3 times 3 minus 2, so that would be 7. A sub 4, because I'm looking for the first 5 terms. Take a 4 and fill it in. And a sub 5, 3 times 5 minus 2 is equal to 13. This would be the first 5 terms in the sequence. So the sequence will go 1, 4, 7, 10, 13. That would be the first 5 terms in the sequence. If you wanted the first 5 terms in this sequence, then you just same thing. Start with a 1, 1 squared, plus 6 times 1 minus 7. So that would be 0, and so on. Take a 2 and fill it in. A sub 2 is blah, and it's right, figure out what it is. Okay? Alright. Recursive formulas. A recursive formula requires that you build on the term that came before it. So let me just list one that came before it. 1, 4, 7, 11, 13. Oops, I don't have it right, do I? 1, 4, 7, 10, 13. I'll just rewrite it on top of that 10. Okay? Without having a formula for this, can you tell me the next term, and the next term, and the next term? Well, you're looking at it, and you see how each one grows by 3? So the next term in the sequence is 16. And the next term is 19. And the next term is 22. You're getting that because you're seeing each time I do this, I'm adding 3. This is recursive. I'm looking at this last term and the known pattern to get the next one. So this is the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth term. This would be A sub 9. If I want the 10th term in the sequence, I have to know the 9th term in order to get the 10th term. You have to know all the terms that come before a term to get the next one, because it's recursive. You're building on the pattern to get the next one. Okay? If I had a third, and the next one is a sixth, and the next one is a 12th, and the next one is a 24th, what am I doing to this pattern? I'm doubling the bottom. So the next term is 1 over 48, and the next term is 1 over 96. I had to know all the terms that came before it in order to get the next ones, because I had to see the pattern, understand the pattern, to know to double the bottom to get the next ones. That's recursive. And a recursive formula looks like this. It looks much more complicated, but it's actually easy because it's recursive. Okay? You just follow the pattern and keep doing what it says. Okay? They always have to tell you where to start. So in this case, they're telling you the first term is 2. All this means here, and I'll explain it as we go, is to get the next term, take the previous term, and add a half. To get the next term, take the previous term, and add a half. Okay, now without understanding the symbology yet, just follow what I said. To get the next term, take the previous term, and add a half. To get the next term, take the previous term, and add a half. Now, why is that working that way? Well, let me show you this. The next term is 3 plus 1. To get the next term, I'm going to take the previous term and add a half. See, this is A sub 4. To get the next term, I'm going to take the previous term and add a half. To get the next term, I'm going to take, give me a second, the previous term and add a half. Here it is. Let me get rid of that. To get the next term, take the previous term and add a half. Whatever term this is, that's one term after it. It's the next term. If I gave you A sub 5, what's the next one? A sub 5 plus 1. It's the following term. To get the next term, take the one that's right before it and add a half. Okay, that's how you do a recursive, and that's how the formula is written. Okay, we'll try some more. All right, here's a famous recursive formula called the Fibonacci sequence. In this one, they're actually giving you the first 2 terms. So the first term is 0, the second term is 1. The third term, to get the next term, take the one right before it and add it to the one before that. To get the next term, take the term before it and the term before it and add them together. Take the previous 2 terms and add them together. Take the previous 2 terms and add them together. 64, bear with me, 55, 89, and so on. Okay? Now it turns out that pattern, and I'll talk more about the counters in a second, show up quite a bit in nature. When you look at the sunflower, can you see these rows, these spirals that are forming right here? There's also spirals that go this way. And then there's also spirals, where are they? Come on, where's the third set? So those are spiraling left, those are spiraling right. I gotta get one more set. Come on. There we go. There's a row that's really steep. And if you count the number of spirals, not the number of kernels, the number of seeds, the number of rows that go one way, the number of rows that go that way, and the number of rows that go this way, it turns out that you get a Fibonacci sequence. Look back up at those numbers. 34, 55, 89. It shows up in nature. Pineapples. You get the spirals that go this way. You get spirals that go that way. And you get these really steep ones. If you count the number of spirals, you come up with 5, 8, 13, which again is back to Fibonacci sequence. All right. So, amaze and astound you by showing you that. Let me go back and talk about these counters, these indices. Okay, so that's the first term, that's the second term, that's the third term, that's the fourth term. Okay, so let me just jump down here. If, how about, I'm hesitating whether to use actual numbers or variables. Okay. All right. A sub 4 is a sub 3 plus 1. You could also call a sub 4 as a sub 2 plus 2. You could also call a sub 4 as a sub 1 plus 3. All I'm saying is, when you look at this, a sub 4 is a sub 2 plus 2. That's right here. A sub 4 is a sub 2 plus 2. So if I used a 2 for the variable, that means I have to put a 2 here. So then that'd be 2 plus 1, so that's a sub 3. If I put a 2 in for k, that means I have to put a value in there. So a sub 4 is a sub 3 plus a sub 2. Let's try a sub 11. That's a sub 9 plus 2. If I'm using a 9 for k, then I have to use it. Oops. I needed to put an equal sign. Plus a sub 9 plus 1. No, sorry, that was an equal sign. That's here. Whoop, I was right. I apologize. Plus a sub 9. To get the next term, take the one right before it and the one right before that and add them together. Okay? We'll work some more with the recursive as we go. Here, find an expression to represent the sequence below. This is assuming that you guys have an explicit expression you're looking for. Another word they'll use with this is apparent. Find the equation for the apparent nth term. That means explicit. So it means a formula that looks like this. You're looking for a formula that looks like this. Okay? So here goes. Try and find, sometimes it's really helpful to me if you write the indice with it. So that's the first term, second term, third term, fourth term, fifth term. Sometimes it's really helpful if you're looking at the number that you're filling in to get these. Okay? Now when I see those, I'm seeing 5 times 4 minus 1. This one, 4 times 4 minus 1. 3 times 4 minus 1. And so on. 2 times 4 minus 1. 1 times 4 minus 1. So the formula is a sub n equals, it would be 4 times the counter minus 1. Try it. Stick a 5 in there. A sub 5 is 4 times 5 minus 1. 20 minus 1 is 19. Okay? I realize that sometimes it's going to be difficult to initially see these patterns, but that's, I'll help you with it. That's all I can say. Is that, to me, a real bonus is to write the indice above it and look for what you're doing that indice to help you see it. Okay? When you guys have fractions, I think what works well, so I'm going to go ahead and write the indices with this, is notice nothing's happening to the top. So you know you're going to have an a sub n is 1 over something. Okay? Now, sometimes the first one doesn't help much. You have to look down the road. You did something to 2 and got 4, something to 3 and got 9. Well, I hope you see it, that it's just n squared. That would be your pattern. Right? When your sequences are alternating signs, well, first off, let me show you this. Negative 1 to the 1 is negative 1. Negative 1 squared is 1. Negative 1 cubed is negative 1. Negative 1 to the 4th is 1. What I'm hoping you're seeing, with even exponents, you get a positive. With odd exponents, you get a negative. So when you're alternating signs, you're going to have some variation of negative 1 to some power. So let's just count it as n for now. 1, 2, 3, 4. Those are the term numbers. I filled these numbers in and got those as answers. What I'm hoping you're seeing is 1 squared is 1, 2 squared is 4, 3 squared is 3, 4 squared is 16. So I have to alternate the sign as well as square the indice. I take a 1 and put it here. That's going to give me a negative 1. I put 1 there. I get 1. Take a 2 and put it in. I get negative 1 squared, which is 1, times 2 squared, which is 4. So a sub n is equal to negative 1 to the n times n squared. It's a horrible n. My goodness. Okay. That's when the first term is negative. When the first term is positive, you guys have to alternate this. Okay, guys, sorry for the interruption. When the first term is positive, so I filled in a 1 and got a 1, 2 and got negative 4, 3, and so on. Your indice, your counter, has to be adjusted by 1. You either have to move it forward or backwards. So what I mean is, you either use negative 1 to the n plus 1, or you use negative 1 to the n minus 1. You have to move the counter either forward or backwards. Then, what comes next is the n squared. Okay? So that's how, try filling the number in for that. So you're either moving it forward or backwards. Okay? Either one of these is going to work fine. It's up to you. If I take the 1 and fill it in, then I get negative 1 to the 0, which you guys should know is 1, times, I filled a 1 in, 1 squared. Okay? If I move it forward, I have negative 1 to the 1 plus 1 times 1 squared. That's now 2, which makes that 1. Okay? So when the first term is positive, you have to move the indice either forward 1 or backwards 1. So it turns that into a positive. One like this, I would strongly recommend that you guys do not try and find a pattern for the entire fraction. Focus on, first, how about the signs are alternating. The first one's positive, so I'm going to need a negative 1 to the n plus 1, or a negative 1 to the n minus 1. It's your call which one you use. You'll see in a second one of them might make a little more sense. Now, focus on the top first. I filled in a 1 and got a 1, 2 and got a 2, 3 and got 4, 4 and got 8. Okay, so what's going on there? All right. Notice that these are powers of 2. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. Those are powers of 2. Notice I filled in a 1 and got a 0. Filled in a 2 and got 1. Filled in 3 and got 2. 4 and got 3. So it's 2. I don't really need the parens. I'm just doing it to have symmetry, I guess. How about n minus 1? Now focus on the bottom. I filled in 1 and got 3, 2 and got 9, 3 and got 27. Those are powers of 3. It's supposed to be a 4. All right. So the bottom is just going to be 3 to the n. Now, if I do the same thing here, 2 n minus 1 over 3 to the n, what you can see is here your exponents don't match. There's no requirement. I would totally accept this as an answer. But noticing here, they're the exact same exponent, and this is a product, I can actually shorten this sucker up and go negative 2 to the n minus 1 over 3 to the n. Again, I would accept this as an answer, but this is also acceptable. All right? So when you're alternating signs, sometimes it's advantageous to push it forward, sometimes it's advantageous to pull it back. Okay, the factorial symbol. This is just kind of a fun conversation with this. What you need to understand with the factorial symbol is a definite, or how about 1 factorial, that's how you pronounce it, it's just 1. 2 factorial is 1 times 2. 3 factorial is 1 times 2 times 3. 4 factorial is 1 times 2 times 3 times 4, and so on. 1 times 2 times 3 times 4 times 5. To get the factorial button, you guys can follow the steps here. You hit math, go backwards to probability, and then choose option 4, and that gives you the exclamation point. So obviously you have to type the number in first, but what I want you to see is factorials make huge numbers. 12 factorial is about 479 billion. Huge, it's huge numbers. Okay? So how to simplify this is, I want you to note for a second that that would be 1 times 2 times 3 times 4, or I suppose you could also call it, and sometimes, sometimes this is helpful, I wanted the eraser, is if you go backwards, 4 times 3 times 2 times 1 over 7 times 6 times 5 times 4 times 3 times 2 times 1. Notice all of that is going to cancel with all that. Now you don't have to write all of this out to do it. I'm going to leave this as 4 factorial. 7 factorial is 7 times 6 times 5 times 4 times 2 times 2 times 1. That is 4 factorial. I can stop at any point and write 4, or whatever the factorial is. So stepping aside, 7 times 6 times 5 times 4 times 3 times 2 times 1. Or 7 times 6 times 5 times 4 times 2, that would be 5 factorial. Or 7 times 6 times 5 times 4 times 3 times 2, it would be 6 factorial. You can stop at any point you want and put the factorial symbol back on. I'm stopping here so those cancel. And you get 1 over 7 times 6 times 5, whatever that's worth. Okay? So down here, when you've got these, you're going to try and break these up. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, so 6 factorial. The 3 factorial I'm going to leave. 4 factorial is 4 times 3 times 2 times 1, which is 3 factorial. And the 6 factorial is still there. These cancel out, this cancels out, and then this reduces. So your answer is whatever 10 times 9 times 2 times 7 is. That can be helpful in doing these. So let's just look at n factorial. N factorial. That's n. Then 1 less than n. Then 1 less than that. Then 1 less than that. And so on. At any point that you want to stop, you can, and put the factorial symbol back on it. Is n minus 1, n minus 2 factorial. Now the reason I'm going to choose that one is because then it matches the bottom. Bam. N factorial divided by n minus 2 factorial is n times n minus 1. No factorial. The factorial symbols cancel. This one would be 2n plus 2 times 2n plus 1 times 2n. Notice these are 1 less each time. Oops, I stopped, so I got to put the factorial over 2n factorial. And those cancel out. So this would be your answer. Okay, that's the end of part 1.